When writing transformations for linear functions, we'll think of it like this. Y equals the slope times x minus the horizontal shift plus the vertical shift. So we can relate transformations of linear functions to what we already learned about transformations of absolute value functions. So if f of x is 2x plus 1, write a function g whose graph is a translation 4 units up from the graph of f. Remember, a vertical translation just means adding or subtracting that number to the end of the function. Now plug in and simplify. And there's our transformation. Write a function h whose graph is a translation 2 units to the left of the graph of f. Because we're translating 2 units to the left, h will be -2. This is when it's especially helpful to think of a linear function in this transformation form, because a horizontal shift should only be subtracted from the x, or the input value. This would make h of x equal to f of x minus whatever h is. Let's simplify that. We're going to plug in f of x, but remember, this 2 is being added only to the x. So here's our original 2x plus 1, and then we add 2 inside. Now we're going to distribute to put this into slope-intercept form. And you can always check by graphing. Does this new equation truly show a translation of 2 units to the left from our original f of x? Yes, it does. Now we're going to practice writing an absolute value function as a piecewise function. A piecewise function is a function defined by multiple subfunctions, where each subfunction applies to a different interval in the domain. Rewriting an absolute value function as a piecewise function will remove the need for the absolute value symbol. And the reason why this is super helpful is because absolute value symbols do make it somewhat difficult to do algebra. We cannot distribute into an absolute value group, for example. There's just a lot of things that we can't do because of absolute value. So being able to write an absolute value function without any absolute value symbols is really helpful when we're moving on to things in calculus. A piecewise function can be defined by as many pieces as you want. But a linear function with absolute value, meaning there's not an x squared inside of here, just an x in the absolute value, can be rewritten as 2 parts. The line that is to the left of the vertex and the line that is to the right of the vertex. F of x is made up of 2 lines. We put this big curly brace to show that f of x is made of multiple pieces, or multiple subfunctions. To the left of the vertex, we have a line with a slope of -1. And its y-intercept is 0, so we don't need to add anything. When we move to the right of the vertex, we have a line with a slope of +1. We are transitioning from the line with a negative slope to the line with positive slope at what I like to call the transition value. And that would be the x part of the vertex, because subfunction intervals are determined by domain, not by range. Meaning -x is defined in this absolute value function whenever the x's are less than or equal to 0. And then our line has a slope of +1 when the x's are greater than 0. You could put x's less than or equal to 0, or you could put the or equal to on this side, just as long as for one of these pieces you still have a point at the vertex. Or you could specifically define that vertex point as a third piece of your piecewise function. Both of these would be acceptable ways of writing this absolute value linear function as a piecewise function. Now our transition value, or the x part of the vertex, is no longer 0. H is equal to 3. To the left of the vertex, Our line has a slope of -1, but it also has a new y-intercept, and that y-intercept is 2. That is when our x's are less than or equal to h. Now to the right of h, the slope of our line is +1. But if we extended this line, we would notice our y-intercept would be -4. So x minus 4. This is the second line that makes up the absolute value function, but it's only defined for when x is greater than 3, our transitional or h value in this case. How else could we write it? Try it on your own and then press play to check. Notice that the y value now, when x equals +3, is -1, not 0, because our vertex has shifted. Our h value, or x part of the vertex, is -1. To the left of the vertex, we have a slope of +2. If we extended this line, our y-intercept would go through also +2. So +2x plus 2, and that is when x is less than or equal to our h value. To the right of the vertex, our slope is -2, and our y-intercept is -2. So when x is greater than -1, our function is defined by the line -2x minus 2. Rewrite that as a piecewise function with 3 pieces. But what if you don't have the graph, and you don't want to graph it out, and you just want to do this algebraically? How would we do that? Going back to number 3, go ahead and rewrite g of x without the absolute value and with parentheses instead. So we're going to multiply the slopes of the first piece by -1. The reason why is because a is a positive number, but our first piece has negative slopes. But when a is a negative number, our first piece should have positive slopes. No matter what, we'll change the slopes of the first piece of our piecewise function to be negative. So even though a is negative in example 4, we will still multiply the slopes of the first piece by a -1, and this should give us what we already got from visualizing it. And we are correct. So you can create a piecewise function from an absolute value function algebraically or visually by graphing. This will make operations of absolute value functions much easier when we can split it up without an absolute value.